So thank you all for coming. This is the 2018 Clay Colloquium. As I think everybody here is aware, one of the more significant benefactors of this observatory were Landon and Lavinia Clay. And the Clays established the Clay Postdoctoral Fellowship in 2000 to encourage and celebrate the observatory's outstanding researchers in all of the disciplines of astronomy and astrophysics. And I think it's worth noting that the first of our Clay Fellows was recently elected to the National Academy of Sciences. Landon passed away in July last year, and it's a very significant loss. He'd been not only a contributor to the Clay Fellowship, his name is on the Clay Magellan Telescope in Chile because of his contribution to Magellan. And his principal philanthropic interest actually was mathematics. The Clay Mathematics Institute was, in his words, his first love. But we did well being his second love. Regrettably, none of the family are able to join us today. Thomas sends his best wishes and regards. Thomas actually has moved from the East Coast and now lives in Boulder, Colorado, and runs a gold mine in California. Was just noting that when Thomas was an undergraduate at Harvard, he started out in physics but graduated in classics, Greek and Latin. But now he's running a gold mine. So, but anyway, let's get to the moment. Our presenter today is Reinout van Weeren, who's well known to many of you because after he graduated with his PhD from Leiden University in 2011, he came to the Center for Astrophysics first as an Einstein Fellow, and then in 2015 we named him a Clay Fellow. He has subsequently returned to Leiden, where he is an assistant professor, and I just learned that his first teaching assignment was an undergraduate observing program where he took 35 students to La Palma for 10 nights on the 2.5 meter. Just like to note that Reinout is exceptionally prolific. He had, I think, 20 papers by the time he completed his PhD, and now has 156 referee papers. His research focuses on radio and X-ray observations of galaxy clusters to study particle acceleration processes. And he also works on low-frequency radio instrumentation, which we'll be hearing quite a lot about today. So with that, I think I'll hand the floor over to Reinout. His topic is galaxy clusters in the low-frequency sky. Thank you.
Great. Thank you, Charles. It's really great to be back here at CFA. Also, the weather really cooperated. No snowstorms, at least in May. So, yeah, I'll tell a little bit what I've been doing actually the last year since I moved away from CFA, but it's actually a continuation from the research I have been doing at CFA. I was already doing low-frequency radio actually at CFA and also before I came here. And this really has now kind of taken off the last year, so I want to kind of update you on what has been happening on that front. And at the same time go a little bit back also to provide the motivation why I'm really interested in low-frequency radio observation, also combining that with other multi-wavelength data. And I should particularly mention these people here at CFA, like Philippe, of course Bill and Christine, and also Raf and Gabriela, because they have been doing some of the work actually, and also a lot of the X-ray work here, and actually Gabriela also some of the radio work. And it's really this kind of combination of multi-wavelength, I think, observation which has made a big difference in the field I'm working on. Before that, people really worked on the radio itself, and they didn't combine it with the X-ray, for example. And that's really one of the things why we can have made so much progress. So I'd like to kind of start with the galaxy cluster, because maybe not everyone is working on that. So this is an optical image of the galaxy cluster ABELL 2744, which is a very massive, disturbed cluster. You can already see that because there are different subgroups present in this cluster. Don't get disturbed by this kind of artifact here. It's an overexposed star. Sometimes people ask me, what is this? It's just a star which was too bright and it's kind of cut out. So this is an optical image of a cluster, but of course, we all know kind of most of the baryonic mass in a cluster is in the form of a hot thermal intercluster medium with a temperature of 10 to 100 million degrees Kelvin, and this emits thermal Bragg-Strahlung at X-ray wavelengths. And that's why you can observe it with X-ray satellites and kind of make these really nice pictures where you can really say something about the dynamical state of a cluster. Here you can clearly see this is not really a round object, but it has a lot of substructure because this thing is a kind of a merging cluster which is still kind of in the process of forming, essentially growing bigger and bigger. Now this is the picture we have at X-rays from a cluster. In the radio, this is how a cluster looks like. So this is roughly at gigahertz frequencies with the VLA. So again, you see this cluster here, and what you see in the radio at these frequencies is synchrotron emission, so we kind of all, I think, know. So we have energetic electrons, which we call cosmic rays, spiraling around magnetic field lines. So if you observe synchrotron emission from a cluster, you know you have cosmic rays present, because these are the particles which emit the synchrotron emission. And at the same time, we have magnetic fields present, and that you can also see if you actually look at the polarization of the radio emission. That actually tells you something directly about the orientation of the magnetic field. The synchrotron already tells you magnetic field is present, something about the strength, but you can actually also measure the orientation. And the fields in clusters are actually very weak, so about a microgauss, and if you compare that, for example, to magnetic fields on the Earth, it's of the order of a Gauss. So these are really extremely weak fields. And that's why we have synchrotron emission at gigahertz frequencies, because that kind of sets the frequency where you can observe the synchrotron emission. So, of course, if you have cosmic rays, the question is always like, where do these cosmic rays come from? Because you need some exotic process to accelerate particles so that they become cosmic rays. So that's essentially the question we are trying to answer. And it turns out it's actually a very difficult and complicated questions. And people work on this for for I think 10, 20 years, quite hard now. And we have made progress, but there's still mysteries here. And we do not fully understand this process still. One of the important things, like diagnostic tools in the radio spectrums are quite boring, they're power laws. But there's one thing you can measure with a power law, that's the slope, and that you call the spectral index. So that's just indicated here. You have a power law spectrum in a log-log diagram. This we call a flat spectrum, the slope is flat, and this, for example, is called a steep spectrum, just to indicate. And this you characterize with what we call the radio spectral index. So it's nothing else than just the slope of the power law spectrum. This we often use because this is one of the few things, besides the brightness, we can measure in the radio band. And it's an important quantity because it says us something about the acceleration and cooling mechanisms that operate on these cosmic rays in cluster. One important thing to notice is that for radio emission and synchrotron emission from cluster, the spectra are typically steep. So something like, which indicated with this blue line here. And what does it mean? That's a very important thing to notice, because that means that at low frequencies, this emission is much brighter than at high frequencies. For example, if you have a typical AGN, they have more flat spectra, while this cluster emission is more steeper. So if you go to low frequencies, the relative brightness between AGN, for example, and cluster emission increases, and it becomes easier to see this kind of cluster scale radio emission at this low frequency. So that's a motivation why we want to go to these low frequencies. And it's really as dramatic as this. You can really go a factor of 10 easily in brightness if you go from gigahertz to megahertz frequencies. Of course, the larger context is like, we kind of know already that galaxy clusters, of course, are not isolated objects. They sit in a large-scale environment, what we call the cosmic web. And these galaxy clusters grow by accreting material from this cosmic web and also actually merging with other objects and galaxy clusters and galaxy group in the cosmic web. And the idea is to explain this kind of radio emission. We think that during this structure formation process, you create shocks and turbulence in these merging clusters. And by some process, these shocks and turbulence then get accelerated and forming these cosmic rays. And here is a toy model of a merging cluster, of a binary merging cluster, so two clusters merging, where you form this kind of outwards propagating shocks. And these are thought to represent, for example, these elongated radio structures you see here in this particular cluster. The simulation was run to kind of try to reproduce this particular cluster. So that's kind of the main idea behind the formation or the acceleration of this cosmic ray. So this, for example, can happen in shock waves, is what we think. Okay, so this is a little bit of background. So I'll go a little bit more in background, introducing what kind of is the open question, what are the problems in this field with this particle acceleration. And I will then switch gear a little bit, talking a little bit about LOFAR, because this is kind of the telescopes which allows us to go to low frequencies, and tell a little bit what we have been doing with this telescope, because we have not only been observing galaxy clusters, of course, there are other interesting things to observe, so show a little bit where we stand and what we have been doing within the LOFAR surveys team. So there's a very big team, mostly European team, of like 200 people in the surveys, where we carrying out a very large survey of the sky with this telescope. And we're just about to release or submit the papers from the first big data release here, so I will show you a little bit what's in there. And then show a little bit of the galaxy cluster results from these kind of initial observations. Right, so if we go back to galaxy clusters in the radio, going back to this picture, here we have the X-ray picture again, you can already see that actually there are different types of sources in galaxy clusters. We see all kind of like point-like objects. These are background AGN or AGN in the cluster often. Here's a nice standard classical radio galaxy. But we see we have these elongated things in the outskirts, so really thin, kind of long megaparsec-sized structures. And we call them relics for historical reasons. We thought these were kind of remnant strip tills from radio galaxies maybe or something, so that's why people call them relic, kind of old fossil sources, which turned out at some point we thought that was not correct, but now we're actually changing our thinking again, and maybe actually it was maybe appropriate to call them relics in some way. And then in the center of clusters, we have this other type of sources, which more looks like the X-ray emission, which you see at X-ray wavelength. So this radio emission in the center we call a radio halo. It kind of roughly follows this kind of broad-scale distribution from the thermal intercluster medium. And we think there are different mechanism operators to explain these quite different types of sources. For example, radio relics are really highly polarized, so you can measure the magnetic field vectors, for example, as what I showed. Well, this is not at all the case for radio halos. And also relics at higher resolution show a lot of substructures, so they're very complicated morphologies. While halos are typically very smooth, just somewhat comparable to the X-ray distribution. And it's interesting to note that all main big radio halos almost and all relics are found in this merging cluster. So this supports this scenario. There's something related to cluster mergers and why we see this radio emission. And one important thing to notice is because he said, okay, we also, of course, know of radio galaxies that have been discovered long before we know of this emission from clusters. And why do we not see a whole kind of bunch of radio galaxies here which all made these things? And there's one important argument which is basically arguing against it. If you accelerate a particle in an AGN, for example, here's a supermassive black hole, you accelerate the particles. If you want to diffuse these particles over a region of it, which is a megaparsec in size, you need a lot of time. You need something kind of like the Hubble time to diffuse them over this kind of distance. And the problem is the lifetime of these particles that are cosmic ray electrons, and they lose energy. They don't live forever because they radiate in the synchrotron band, and they lose due to inverse Compton losses. So they lose their energy. So over time, roughly like 10 to the 8 years, really the maximum lifetime of such a particle, kind of have lost all their energy and they're gone. And in 10 to the 8 years, you can only diffuse over a small region. So you cannot fill this entire volume of a cluster with cosmic rays just diffusing them out of AGN. So you need some kind of other mechanism to accelerate them essentially at their location where we're currently observing. That's kind of in situ acceleration. That's a very important observation because that kind of limits the possibilities how to produce these cosmic rays. And of course, I already said, so we know also of radio galaxies, and this is a classical picture of Hercules A, which is a very nice symmetric radio galaxy. Here the supermassive black hole, the jets, and then you have this big lobes of radio plasma. So in galaxy clusters, typically radio galaxies do not look like this. So there are, of course, AGN and radio galaxies in clusters, but they look more like this. And why is this? That's because the intercluster medium has a non-zero density compared to a lot of these field kind of galaxies. And because these galaxies move with typically like 1,000 kilometers per second through the cluster on kind of orbits, and as ICM is there, they kind of like, this pressure difference essentially bends this tail backwards. And depending on how fast these things move, depending even if the cluster is undergoing a merger event, you have all kind of complicated cluster weather, what people call it. And these radio tails, they feel this cluster weather, so they bend in all kind of interesting shape. And people have actually said there's a whole bending sequence where you have more irregular source, and in this case you think the faster this source moves, the more backwards these lobes bend. And yeah, these things you can often find. Every galaxy cluster almost has some of these kind of weird bent radio sources, and you hope to can, for example, use that to learn something about motions in the ICM or motion of the galaxy. It's difficult, but people have attempted to do that. So this is another component of radio sources in galaxy clusters. So what are the questions? So going back to the big question. So of course I said, how are the particles' acceleration is really a very big main question. So there's shocks. There's also turbulent motions, which can also accelerate particles. We can ask a question about the acceleration efficiency and the maximum energy these particles can achieve. This is quite relevant because actually a lot of theoretical predictions say the acceleration efficiency is quite low. And somehow that's not correct because we see actually quite a lot of cosmic rays in galaxy clusters. So that's an open question. And then of course there's all the properties. What are the really detailed properties of the ICM itself? And can we learn something about that by looking at radio observations? So about shocks and, for example, turbulence and also magnetic fields in the intercluster medium, because these are very hard to often study at X-ray wavelengths with current telescopes, because you need, for example, counts. To measure a shock, you need a certain amount of counts, and it's often quite difficult if the shock is in the cluster outskirts. And for example, to measure turbulence, you need very high spectral resolution, which we don't have at the moment to do that. Although we had Hitomi, but that doesn't work anymore. But that would be a way to measure turbulence, for example. And then, of course, there are questions, how important is this non-thermal component for the overall energy budget of clusters? And this is relevant for precision cosmology. If you have some other form of non-thermal pressure, and you try to, for example, measure the mass just using X-ray observations, you might get the wrong answer if you don't take into account these other forms of pressure. So, a few slides about these different sources. So, how we think we can explain what sort of acceleration mechanism could be at work here. So for radio relics here, we think actually this is shock acceleration, or some form of shock acceleration. And there are two classes of models here. It's a standard, what we call diffusive shock acceleration. It's something what happens in supernova remnants, for example. You can also see them in the radio. And that's where essentially particles scatter back and forward across the shock front. And each time they do that, they gain a little bit of energy from the shock front. And if you do this, you can create a population of non-thermal particles, which are essentially then cosmic rays. And in this kind of default model, you start from a thermal pool. So what does this mean? So that are actually the electrons, which you see at X-ray wavelengths, so KeV type of energy. So you accelerate those electrons, and then you make them into GeV cosmic rays. And this is actually hard, because you start with KeV electrons. They're not so energetic. And this is what people sometimes call the injection problem. And if you have low Mach number shocks, we think actually this is not very efficient. Because we don't have Mach number 10 shocks in clusters. We don't see them. They're low Mach number. And theory predicts that, acceleration efficiency is not very high for such shocks. So this is a bit of a puzzle. So there's an alternative kind of model which works a little bit the same, but the main difference here, we don't start from the thermal pool. So we can, for example, speculate maybe in clusters there are already some energetic particles present from other previous events happens, maybe even radio galaxies dumped some cosmic ray electrons. So they're already relativistic, but not super relativistic. And these kind of particles are much easier to accelerate because they already have gamma factors of like 10 to the 2 or 10 to the 3, some kind of high Lorentz factor. And those you can quite easily accelerate if you then pass a shock through the medium. So that's a kind of alternative model, which then kind of solves this problem starting from the thermal pool. So we don't start from the thermal pool. And why do we think particles are accelerated at shock? Just very briefly, this is a textbook example. We know that because we see kind of all the evidence in the radio why this links to shocks, and also by observing at X-ray wavelengths, but I here mainly focus on the radio. So just taking this particular relic here, this is an arc-like structure, like a shape of a binary merge, what you expect for a shock, where you can, this is a very big thing. I always like to show this, just to show like, these are big particle accelerations, so they're really big structures on the sky. So big actually that if you could observe this by the naked eye, these things would be as big as a quarter of the moon, for example. So they're physically big things, although they are located at like redshift of 0.1, 0.2, 0.3. So they're huge things in the sky. They're not small things. That's why you can, because of this comparison. So they're really big structures. And these are supposed to trace this outward traveling shock wave, which you generate if you put essentially bump two clusters in each other. And then you can accelerate particles, for example, via this mechanism here. And then this mechanism is diffusive shock acceleration. It does pick one. In that case, there's an interesting relation between the Mach number of the shock and the spectral index. So they're linked together in this theory. So you accelerate particles here, and then in the downstream region, these particles just cool. So there's nothing else happening with them anymore. So they radiate. You can see them in the radio band, and they radiate, so they lose their energy. So over time, they slowly fade, and that's why their radio emission fades here and then disappears. So this is this kind of shock downstream region here. So because we have these energy losses, something interesting with the spectrum happens, of course. So if you have energy losses with synchrotron radiation, you get spectra. So this is a freshly accelerated spectra, a spectra which has undergone energy losses over time, steepens and curves. So by just observing the slope of the synchrotron emission at this different location, as what we've done here, this is a spectral index map, you can see there's a very strong gradient from flat spectra to kind of steep curved spectra in the back. And that's essentially showing these energy losses in this outward traveling shock. So that's what indicated here also with the different colors here. And at the same time also we see very high polarization. And if you have high polarization, typically you can create that if you compress even a medium with random ordered magnetic fields. So you create this aligned magnetic field vector, so indicating shock compression. So that's from the radio perspective why we think these things are tracing shocks. And very important is this has been, not in all relics, but in some relics this has also been followed up and confirmed with X-ray observations which actually have measured the properties and the Mach number of the shocks, showing that this general picture is roughly correct. So these relics really trace shock fronts. We kind of know that, and that we didn't know 10 years ago, and I think now everyone is fully convinced of that. And actually to just show some preliminary work, so I showed some kind of crude spectral index map here, but we can now actually study with the upgraded VLA, and this is work of Gabriela who is sitting here, we can really study this kind of gradient in really great detail. So this was yeah, this is really stuff from the last year where we used the upgraded telescopes to do this really in exquisite detail where we can look at variations across this whole big structure to see how this aging and cooling trend essentially works. So I also said there's one interesting other piece of evidence which was kind of found recently. It was last year. This was work I did with Philip. So what we also showed is actually that, not surprising, if you have a radio galaxy just at an unfortunate location for the radio galaxy, close to a shock, and if the shock goes to this radio galaxy, it can actually re-accelerate some of these particles from this radio lobe from the galaxy. Of course, that should happen if this radio galaxy is present, but it had never been really observed. And this was the first case in this merging clusters here, where we see kind of a radio galaxy here with a very bended radio galaxy, where a jet comes out and it ends up in this RELICS here. And at the same time, we find some evidence for a shock here. So we see that these electrons from this radio galaxy can also interact with a shock. So essentially re-accelerate these particles. We don't know how common this is. This is one of the questions we want to answer. Can we explain all RELICs in somehow this way? And I'll go to back later because that's one of the motivations we have for LOFAR. And this is a X-ray surface brightness profile which indicates the presence of a surface brightness discontinuity, which we think is a shocks, although we have not measured the temperature jump because that's what you need to confirm it. There's not enough counts simply here in the pre-shock region. Then 2 slides on halos. So radio halos are quite different in terms of their formation mechanism. So one of the important things for radio halos is to also note that they're also found in merging clusters. And if you divide clusters in this diagram, so you can essentially characterize how concentrated clusters are. So that's the concentration parameters. Here you have very concentrated peaked galaxy clusters with a very bright core. And you can also measure something about the asymmetry of a galaxy cluster. So here we have the bullet cluster, which sits in this part of the diagram. And here we have a very relaxed cluster, which sits in this part of the diagram, is that most of the radio halos, so that are red points, they're always sitting in this merging cluster. So mergers are really a critical ingredient for radio halos. And what we think is actually that this merger generates turbulence throughout the whole ICM of the cluster. And this turbulence is also, although inefficient, is also a mechanism to accelerate particles. So here you also need some form of seed particles. You cannot accelerate this kind of thermal particles. You also need some kind of population of cosmic rays already present, sitting there waiting for you. But when you then have a merger, you can accelerating by this turbulent reacceleration mechanism, what it is called, this MHD turbulence. And I think also over the last year, it has become clear, probably this is the preferred model. There was another very different model here, which is called the hadronic model. I won't go in detail. I think that's by now disfavored by observations. That, for example, doesn't predict that radio halos occur in merging clusters. They should occur in all clusters. And that's clearly not the case. They really preferably live in merging clusters. So if you can see, this one important ingredient here are these kind of what we call the seed particles. So we need kind of a sea of particles in the clusters, which are already kind of relativistic. So they're not gammas of 10 to the 4, 10 to the 5, what we see at the radio, at the gigahertz frequencies. But they are particles which like gamma factors of 10 to the 2, to 10 to the 3, to 10 to the 4. So they're kind of these lurking populations which sit in the ICM of the cluster. And they do not emit at gigahertz frequencies, right? Because the energy kind of sets together with the magnetic field, sets the observing frequencies. So they sit in clusters and they are kind of hidden if you look at them with the VLA at gigahertz frequencies. So if you want to observe this hidden population, these only start radiating at megahertz frequencies and below. Now we cannot go, sadly, below megahertz because the ionosphere blocks that, and even the interplanetary plasma at some point start blocking that. But we can go to kind of the megahertz regime, not below that, to kind of see the tip of the iceberg of this kind of like maybe sea of particles which should be out there. And that's the whole motivations to go to really as low as possible as we can at low frequencies to kind of start seeing if we see this population. And we can then address the question, for example, where's the sea coming from? Where are all these fossil cosmic ray electrons of gamma to the 2, 10 to the 4? Yeah, where do they came from? Because that's an open question, because somehow they also need to have been accelerated because they're cosmic rays still. And yeah, of course, can we observe them? Very simple question, so we should just try. That was the motivation. And so go to low frequency, so that's my motivation. So again here, there's also, we want to essentially see, this is what we see with the VLA, this active AGN, supernova remnants, young cosmic rays. And we want to see, what is this iceberg? How deep does this iceberg go? What is living there? And there are other interesting things as well here. There's also coherent plasma processes, like things like if you have aurora on Earth, it also generates very steep spectrum low frequency radio emission. So if you, for example, want to detect exoplanets, you also want to go as low as possible. For example, the Earth radiates very strongly at megahertz frequencies. Aurora emission, Jupiter as well. So that's another motivation why you want to go there. And you can see this very low energetic component of cosmic rays. So here again, this same kind of cartoon-like picture here. Okay, so that's what we want to do with LOFAR. So I now have I previously had some slides to introduce it, but now I found this great movie, Astron, which is the organization which runs LOFAR and build LOFAR made, so I can make use of that. Makes my life much easier because you can kind of see, because it's a bit weird telescope. So this way I think is a very nice illustration of what is this telescope. So it's in the Netherlands, so there's a lot of swampy water and grass and no mountains. So first thing, and you can kind of see all this kind of weird antennas sitting on the ground. This is made from a drone. You see two types of antennas here actually. So these and these types of antennas. This is how it looks from the ground roughly. And we mainly use these antennas here. So that's the antennas which work roughly above the FN band. And there's also very long baselines which in Europe, so you get also great resolution at low frequencies. So it's a bit of an odd telescope, but it's very electronic. So everything is kind of combined in a supercomputer to kind of simulate a real telescope. And that's very. So this is the telescope where you can really go to low frequencies. And this has only become possible to do that kind of on a grand scale because we have very powerful computers which can combine all the individual signals from this antenna in a computer to kind of simulate a dish. And if you have the VLA, for example, you don't have to simulate the dish because the dish is doing all the work for you. It just puts everything in the focal point. And this thing doesn't put it in the focal point, but the computer is doing that for us because we record all the signals. And once you record the waves, because here you can really record the waves, you can just do your optics equations inside the computer. So you don't need a dish or a mirror to do your optics. You just let the computer do it. And that's great because you have full control. You can do adaptive optics, all kind of fancy stuff just in the computer because you record a wave. So that's what we're trying to do. And we need that. We need that to do that in the computer because we have very nasty problems. And that problem is what we call the ionosphere. So as I indicated here, below 10 megahertz, you can forget it. Everything is blocked. At the gigahertz, things are fine. Radiation goes straight to the ionosphere. But around 100 megahertz, where we're trying to observe, you get this nasty kind of intermediate regime where you get refraction, bending, and it blurs and distorts your radio image. So you have to kind of uncorrect that, like what you can do with adaptive optics, essentially, in the optical. And just to illustrate the challenge, so essentially, I like to kind of show this kind of simple way. Normally, if you look to a cloud, it looks like this. If you go at the bottom of a swimming pool, look at the same clouds, it looks like this. And that's essentially what you can think of the ionosphere as being the swimming pool kind of thing. So that's what we're trying to correct here. And that actually, you can actually really make actual movies of sources. So if you just focus on the position of the sources under a quiet and wild ionosphere, you can see this kind of sources dance around. And this is at 3 arc-minute resolution, so very low resolution. This is same as the human eye. And can you see at that resolution, sources move around. So sources move around by arc-minutes on the sky at this frequency. So if you want to make a sharp image of arc-second resolution, you have to make huge corrections because your sources are dancing over your field. And that's the problem we have to solve, and which was very challenging to do. But we can do that, and this is the difference it makes. So this is if you don't correct for anything, it's a blurry mess. And if you do this kind of adaptive optics corrections in your computer, there's also multi-conjugate correction. So there are different corrections in different directions. It's not only one correction. You can really make these sharp images of the low-frequency sky. And by employing this now on a kind of more massive scale, we're actually using this to kind of do the LOFAR kind of all-sky survey. And that survey has the name LOTS. It's kind of I like the name because, yeah, we are detecting lots of sources. So that's kind of it's called the LOFAR 2-meter sky survey. And this is using this kind of antennas which you saw in this picture. I can show that here, which are grouped in this kind of tile. So there are two different types of antennas which you saw. So here we're using these antennas here. And the reason is that this is above the FM band where the ionosphere is a little bit more well-behaved. So things are a little bit easier. We're still working very hard on the part below the FM band because the ionosphere is just such a pain there still. So we're using these antennas here. And this is the kind of status of this survey. So the first data release, which will come out this year, is just this part, this pointings here. We already have observed this red pointings, and then this yellow type pointings is what we are planning for the next observing cycles and which has been approved. So you see, we're not up to full sky yet. So this takes many years to build up. And the reason is that per pointing, we do 8 hours of integration time. So that's very deep pointings, but then we're doing this all sky. So you can imagine we need a lot of time. Although, as I say, we use multi-beaming, so we put different beams on the skies. At the same time, we observe different directions, but only 2 or 4. This is just limited by computing, so we can only build up area at a certain rate. And this gives us like 5 arc-second resolution. This kind of noise doesn't say too much, but I will show later how it compares to previous processing. And the other big step we made over the last year is that we are doing a lot of the processing now on grid-based infrastructure. So before that, we were trying to download the data. I have tried to download the data to CFA, and I managed to download one data set in my time, 5 years at CFA, and reduce this data set, and I got some nice results out of it, but it's just too slow, because if you have 3,000 pointings, it's just too much data. So what we now do is we actually have processing next to the archive in the supercomputing center, where we can grab the data very quickly from the archive, don't have it to send over gigabit links to a university, much faster links, and we do the pre-processing there, and then it's much smaller, and then we transfer to Leiden or to another place where we can do the processing. So this made the difference why we could suddenly process a larger number of fields. And before that, we're trying to fight this download problem and trying to reroute the network in the building, and in the end, it's just too painful. So we do this at the supercomputer processing center. And where does this if you compare this survey, it's really quite astonishing what this is. I mean, this is really an amazing step. So this is more or less putting all the big radio surveys on one plot, what has been done in the past. And the size of the circles is the resolution of that particular survey. So a big circle is not good, big is bad here. Big means a very blobby kind of resolution in that sense. And so the small circles here, this is 5 arcsecond, this is the LOFAR survey sitting here. So this is the current state of the art where the lot survey is living. And you can see it lives far below any kind of, these are all planned surveys actually, these are planned, it's not being done. This thing is being done now, it lives far below what people have done before. And one important thing is to look at the scaling here, so don't draw flat lines in terms of sensitivity, because we have singleton emission at this frequency. So a typical source has a minus 0.8 slope, so this is a typical radio source. So you have to kind of draw this kind of like slanted lines here to roughly see how much deeper you are with respect to previous surveys. So we go roughly here 2 orders of magnitude deeper, plus the resolution, because you can see this thing is it was the best survey in the same frequency band. This is also still LOFAR. It's essentially living here, so you can see this enormous improvement, sensitivity and resolution here. So this allows us really to essentially do deep fields at every full sky essentially in the radio now. And how does this look like? This is a small part, cannot see many sources, but this is a lot of pixels. So this is just a zoom in, some interesting sources here. To zoom in, some other interesting sources here. So there are tons of sources. And here's actually a more scientific, this goes into the data release paper, so it's not out yet, but this is just an illustration of the quality of the data and what we can see. And does anyone know this galaxy? People should know here, we are astronomers. Yes, it's M51, it's a very famous galaxy, but it looks like a galaxy also in the radio now. This is really nice. Yeah. These are complicated AGNs, and I think these actually live in a cluster, so that's why you see these weird tails actually. So this is just a collage of some interesting sources. And just to illustrate kind of the improvement here in an image base, so this is the lot survey, so this is one kind of field. And now I start comparing it to the first survey. That's probably, people are very familiar with the first survey. That's 1.4 gigahertz done with the VLA, 5 arcsecond resolution, very nice. It's kind of the best survey. It's not all sky, but large fraction, 30% of the sky. And we now compare this survey, and you can see essentially what improvement we make. Sorry, the alignment is not perfect. I tried it, but it's some projection in AstroPy. So you can see the difference it makes. So suddenly, how many more sources we're seeing, and also we're suddenly picking up really diffuse big sources. That's something first is missing. It looks straight through this galaxy, for example. It picks up some bright knots. So it's really like, you see many more sources and also this really big AGN or galaxy. So it's both includes high resolution, but also sensitivity to really big structures like galaxies, for example, or galaxy clusters for that reason. And also together in this first data release, we're not only releasing this radio catalog, but we also worked very hard on finding optical counterparts to the radio source, because a lot of the work, of course, is AGN related, where you want to have the optical spectrum, the redshift, the mass of the galaxies. And that's a lot of work. So we're using here also a universe zoo, so radio galaxy zoo. This is only used by us actually, not by the general public, because we didn't trust them yet. So this was internal testing. So with 30 or 40 other people last year have done a lot of clicking. So for example, this is a classical radio galaxy where here's the core, and there's these 2 lobes. And if you just release the catalog, you think there are 3 sources, but there's not 3 sources, there's one thing. So you have to associate that, and then the user can click and associate it, and then even find the counterpart of this radio core here in the WISE survey. So we find actually counterparts for 73% of the radio sources, which is a pretty high fraction. Of course, we don't look at all the sources in the catalog, because here there are already 300,000 sources in this small data release here. So that's too much work. So we have a whole elaborate scheme to automatically decide and only send roughly less than 1% to the human for classification. We had to work very hard on getting that to a very low number, because this is a very large number. So to try to do as much as possible automatic, but at some point you get very complicated sources, and the human is still better of doing that. And it also has really great positional accuracy, so 0.2 arcsecond if you compare this with tensor. So really, if you have a radio source, the position, you can really reliably match that to an optical counterpart. And this is things you can do this very quick. So we also have like photometric redshift for all these sources using WISE and a Penstar, so they're pretty good here. You can actually even kind of have this radio color diagram. So this is a diagram where you can plot powerful radio sources here in red versus the optical color of a galaxy. So here we have red galaxies, here we have blue galaxies. This is the absolute K-band magnitude, so that's kind of the mass of the galaxy. So here we have massive galaxies here, less massive galaxy here, and we see these different populations in the radio. So here we see AGNs, here we see radio emission from star-forming galaxies, for example, which kind of directly comes out in this very simple plot, where people have worked really hard before to kind of get this out, but it just comes out kind of automatically now. It's kind of really nice to see. This is also very interesting. So from all the AGNs we detect, we counted like how many of these AGNs are infrared selected AGNs, because of course, what we actually see is, to my surprise, because I like to look at X-ray because I came from CFA, only a very small percentage of our radio detected AGN have X-ray counterparts, and that just tells us that we lack a deep X-ray big survey. So this is just relying on ROSAT because that's the only thing which has all sky coverage. So, and their optical, we have now much better coverage. So we're really lacking something in the X-ray here. So we find only 2,000 X-ray counterparts to our many radio sources. So that will hopefully come. What we also did, this is work of a master's student, actually. We thought like, okay, what about machine learning? Because you have so many radio sources. Now we have 300,000, but if we have the full survey, we have roughly 10 to the 8. So what about finding interesting sources? Like how can you find them out of such a survey? Because you cannot look anymore at the images. So yeah, this might still be possible at 300,000, but okay. So we actually used machine learning and self-organized map to kind of see what you could do here. And that's some interesting stuff here. So he built an artificial neural networks, unsupervised learning here, where you have a lot of Fitzfuzz input images. You cut out all your sources, then you put it in the self-learning algorithms, and it builds this kind of things of prototypical sources, so classes of sources which somehow represent an average property of the radio sources, all the variety you have. And then you can do really interesting things. For example, this is the class of prototypes from the self-organized maps. You can then, he made this web interface, you can click on a source, and you can then find in the whole survey the 10 sources which, for example, look most similar to that type of source. And yeah, here you see, for example, all selected kind of double lobes with kind of a little bit asymmetric brightness distribution. Here's a different, this is more like a compact double lobe. What it exactly makes up here is a bit out of your control because it's machine learning, so it kind of tries to figure out by itself what is a good way of representing radio sources. But you can do interesting stuff. You can also ask the question, just find me the 10 weirdest sources which do not look at any of the prototypes. And that's what he's done here. So he classified this kind of the distance, how close a radio source looks to the prototype. So there are many radio sources which looks like prototypes, so double lobes, there's so many double lobes. Close to a prototype. But for example, here are two very exotic outliers. You can see that one of the sources here. So, for example, anyone idea what this is? This is actually a galaxy, a nearby spiral galaxy, I think, where you see the star-forming regions in this galaxy and supernova remnants in this galaxy. So this was picked up. So, and they didn't have a prototype class for that. And these are all weird tilt sources. And this is actually also a very interesting source. This is probably a restarted AGN where you have two lobes from a current outburst and there are two symmetric lobes from an older outburst, essentially. So it found that source. So this is still under development, but it's an interesting way to kind of mine this kind of huge data set in the future to find the thing you're looking for, essentially. So now going back to galaxy clusters. So for galaxy clusters, we're trying to find this fossil plasma, right? They're going back to the seed. So these particles which really emit only at megahertz frequencies and do not emit at gigahertz frequencies. So the first cluster we observed was the toothbrush cluster. So here there's a LOFAR Chandra combination. It looks very nice. But this cluster actually, at low frequencies, it looks very similar to the cluster at high frequency. So we didn't see evidence for some new kind of hidden populations which suddenly showed up in the LOFAR image. So this was the first object we observed. So we thought, okay, yeah, let's try a few more. Another interesting cluster where actually this picture is very different is the cluster ABELL 1033. It's not a famous cluster at all. It was just in the survey. It has this interesting wide angle tail here, which kind of the tail fades, and then it has this two weird parallel futures here. And the interesting thing is if you observe this thing with the VLA, deep VLA observation, the cluster looks like this. So in red is the radio emission, in blue the Chandra emission. So this is how the thing looks at LOFAR, and this is how it looks with the VLA. And now pay attention to this kind of two parallel things here. This is really strange, because we can actually calculate the spectrum of this emission, and this is -4. And then you think, okay, -4, -3, but does it matter? But a spectral index of -4, it means a source is 10. So if you go from 1 gigahertz to 100 megahertz, so a factor of 10, you go a factor of 10 to the 4 in brightness. So this thing suddenly is 10,000 times brighter at low frequencies. And so you completely miss it at the VLA. And the interesting thing is, if you want to detect this with the VLA, because we know it's there, it will take you 100 years. So that is what spectral indexes 4 means. So this is really hidden at high frequencies. If you lose the thing, it's gone. You will never detect it. So this was kind of the first real cluster where we saw evidence for kind of a new type of source with a really steep spectrum. So this is really some of a fossil population. And the strange thing is, it's not probably a very normal, it's a special fossil population, because the weird thing is you have these tails, it fades, gets fainter, so it gets steeper, but suddenly it brightens. So that is strange. It's still steep, but it's brighter. So there must be somehow another mechanism which boosts this brightness. And it's still unclear. So we call this, Francesco was led his work, call them GREETs, so gently re-energized tails. So there's some mechanism which re-energizes them, but we don't know what that mechanism is still. So there's some form of things which flies some form of fresh energy to these electrons, but still keeps them at a really steep spectrum index, so this really steep population. And yeah, we don't know what it is. So is this a rare example? And I think by now we started seeing it's not. So there's another very unfamous galaxy cluster, ABELL 1933. Nobody had looked at this thing before, but it was in the survey. So this is how it looks like in LOFAR, not very spectacular, but there's this weird thing sitting here. And we also had a very deep VLA observation of this cluster, and this is the VLA image. Actually, this VLA observation is much deeper if you look at point sources. And you can see this kind of, again, this kind of thing just showing up at low frequencies and not a hint of it at the VLA. Again, indicating this is very steep spectrum. And it's pretty big. This is, I think it's almost half a megaparsec in size. So it's a big thing in this cluster, and it's completely hidden at high frequencies. This is an optical overlay on the SDSS image. So here you see the BCG of this galaxy cluster. So it's sitting kind of next to the BCG, kind of lives here. And this is a Chandra image. So this is a really low, massive, boring, I mean, nobody had ever dared to look at this cluster, had even no reference in NED. But this is a very short, shallow Chandra observations, which we took to get a rough estimate of the temperature of the cluster and the mass, just to get some indication what kind of cluster is this. Turns out it's really like a wimpy 10 to the 4. It's almost like a group. So it's not at all a massive cluster. So even somehow in this really low mass cluster, we have a very big, like half megaparsec population of fossil plasma sitting there. And so what could this fossil plasma be? So what we think actually is that this is just a remnant, an old, probably remnant of a lobe of this BCG, which kind of, and we try to estimate the age by looking at the spectral index. So you can compute the spectral index as a function of the lifetime essentially of this AGN. And we observe a spectral index of roughly -3. So then we assume, using this model here, there's a particular model here, that the source is roughly 200 mega years old. So this is kind of an old, probably a lobe from an old outburst from this central AGN. That seems the most logical explanation. So yes, indeed, there is evidence that these kind of fossil populations sitting in clusters there. If you start looking at low frequencies, you see this tip of the iceberg appearing. And there's one more example, so actually we found more. There's also this cluster ABELL 2034, which at high frequencies looks quite boring. At low frequencies, again, we see this fossil population pop up. This is, again, a nice color overlay with the Chandra image. And what we also think is that we see signs of interaction of this fossil lobma with merger activity, because in merger you get large-scale motions of ICM, which probably creates all this kind of complex interactions between this tail and this radio plasma. And there's finally, go back to this image here, also even in this cluster, which was very well studied in the radio bands, the best studied clusters in the radio bands, everyone's favorite target because it looks so complicated. Even in this cluster with LOFAR, we see this kind of new source popping up here, which is not visible in extremely deep VLA observations, and this has also a very steep spectrum, so something like -3. So it becomes kind of a common picture that, yes, we see kind of, I think, with the tip of this iceberg. And that is preliminary, because this is just a handful of clusters. We don't have a full sample yet. We really want to quantify this. But yeah, I think there's evidence that really galaxy clusters do look different at low frequencies. And there is a kind of new population which shows up. It's just not an extension from high frequency observation. There's new stuff there. So this is my summary. I will have a brief outlook here where we want to go from now. So we have seen that galaxy clusters are particle acceleration, and there's a big question about the seed particles, because from the theoretical models it has become clear that we need this kind of sea of old kind of fossil cosmic rays living in clusters kind of hidden from view, which suddenly start becoming important when you have a galaxy cluster merger event. So when you have shocks and turbulence passing through this medium, you suddenly boost and re-accelerate this population and it becomes visible with normal gigahertz radio telescopes. And so we're using this deep new LOFAR radio survey, and I should advertise this here. I think today these papers are submitted to ANA, the first 3 papers here, and we're planning for a special like 20 paper ANA issue, which describe many more things, not only galaxy clusters, but also AGN studies on this survey. And this is data release 1, which is still a very tiny part of the full data set, as you saw, so there's still a lot more to come there. And I think also what we see is that, with LOFAR now we see evidence of this kind of new population of cosmic rays, this low energetic cosmic rays, fossil cosmic rays sitting in clusters. So where we want to go next, so it's quite easy, we start going to the iceberg. So we actually, at LOFAR we're looking at the tip of, well, not the tip we see at the VLA, but we're looking just the part below the water. So we're kind of exploring this part, and that's because we're using this LOFAR high band antennas, this kind of tiles on the ground. So this is above the FM band. The FM band ends at 108 megahertz. And that's where things are the easiest, where the ionosphere is the quietest, where we have the greatest sensitivity. But of course, we want to go down in this iceberg as far as we can do from the ground, at least for now. So we want to go down. So how do we go down? Well, we have to go to lower frequencies, so below the FM band. And actually, LOFAR has antennas there, so these are these low band antennas. They go from 10 to 80 megahertz. And we have not used them yet because it's so challenging, but that's where you want to go if you want to go deeper and see even older cosmic rays, essentially. And this is essentially how we think this is going to do. So we requested the funding for a LOFAR upgrade. This is under evaluation for a major upgrade. So what we're going to do with LOFAR, we are now in this situation here. At the high band, this kind of tile sinks, we can go from this poorly calibrated images now to this really nice images rich in science. So that is done. We're now doing this big all-sky survey to kind of take advantage of that. But what we now want to do in the low band is do the same. And we're using these antennas which are already in the field, so they're already there. What we're just going to do, we're going to upgrade the electronics, because at the moment we are very limited on how many of these things we can use. And that was done to save money, because electronics is the most expensive part of this telescope. So we now ask for extra funding to essentially use all the low band antennas we have available at once. So we essentially increase the sensitivity of our telescope, making calibration easier. What we're also going to do, the other problem is that in order to combine signals from many antennas, you need to combine them at the right moment, so in phase. And of course, it goes with the speed of light. So if you have a station in the north of the Netherlands, 100 kilometers apart, you combine it with another station in Germany, for example, the signals have to come together at the right time. For that, you need clocks, essentially. And we're using some kind of low-cost GPS clocks at the moment. They're not very precise. And that's also what we want to upgrade here, so that we get very precise clocks so we can better combine the signals. And most importantly, I think the most exciting thing is that we're going to do this. So we're going to upgrade the electronics that we can observe even simultaneously with this and this antennas. So these antennas, we already kind of solved the problem. We kind of can model the ionosphere in these high-band antennas here. So once we have these models are such that we can extrapolate these models to low frequencies. So we use the higher sensitivity, higher frequency observations to derive the model and then apply them to the simultaneous observations at the low band. And the simultaneous is very important because the ionosphere is so dynamic. It changes on 10-second time scale. You have to essentially observe simultaneously. So by this essentially electronic upgrade, we're essentially upgrading the brain. We hope to be able to kind of also start using this low-band antenna. And then finally, one other thing we're planning to do and we're working on is a very other exciting prospect. So this is, again, this LOFAR all-sky survey. And I said we roughly get 5 arcsecond resolution, which is great because it means positional accuracy of 0.2 arcsecond. But we all know that radio is kind of known for higher resolution observations. And what we do at the moment, actually, we're only using the data from the stations in the Netherlands. The Netherlands is not so big, so roughly 100 kilometer baseline stations. However, all this data, as much as possible, is recorded with all the information from this international baseline. So this data is going into the archive. It's sitting in the archive. It's just that our computers at the moment are not powerful enough to really process this data on a massive scale. But that's what we're working on. And there we, again, did this kind of massive grid infrastructure probably for, to also start using all the information which comes down all the time from these international stations all over Europe. And that will allow us to go to 0.3 arcsecond resolution if we can combine that. So the data is in the archive, it's waiting there for to be mined. So that's the other goal for, I think, for the next couple of years, to also utilize the data and learn how to deal with it, essentially. That's the thing. We don't know exactly yet how to do that, but there are ideas, and that's what we have to explore. People can already do this for like one observation, one pointing. if you painstakingly work with that, people have done this successfully. But how can you do this automatically for an all-sky survey? That's the more difficult question. And with that, I'd like to answer. Yeah, that's essentially the upgrade. So now we go from the Netherlands to the whole of Europe here. And thank you for your attention.
Most of the other novel radio telescopes end up in locations like northwestern Australia where there are no cell phones and televisions. And the Netherlands has a lot of that stuff. And you didn't mention any of it. Is it really insignificant?
That's a very great question, because this was the first concern when the thing was built. This was the first thing people raised. Like, okay, no, don't do this because this is stupid to do. And it turns out actually this is not the biggest problem we have. So we can, there is interference, but we can take it out quite automatically. It's only a few % of the band which is affected by this typically. So for now, actually, this turned out to be one of our least problems we worry about actually. So it's quite easy to deal with it. The only concern is that people like windmills and green power, which I support in that sense, but these things can reflect, they turn, and they're big, they're 100 meters high by now, and they're building more of them, so they can reflect radio waves from quite far away and then bounce them into your telescope. And because these things spin, it's kind of a messy thing if that kind of reflects in and out. So that's a little bit, we see some interference from that. We actually use that to press the government to say we need more funding to build more electronics so we can suppress this thing actually. So we're trying to also upgrade some of the electronics to better suppress this signal actually, because you can do things of suppressing, but at the moment we see some of this thing leaking in. It's not a big problem, but if they start building more, it might become a problem. And there's one other thing. If you're interested in a spectral line like the epoch of reionization, and this line is located in the FM radio band, then you should not be in the Netherlands, for example. Then you have to go to West Australia, so it depends a bit on your science. But some things we avoid, some parts of the band.
Okay, thank you.
Yeah.
Questions? Igor?
Yeah, I have a question about that structure that you detected in one of those clusters which you attribute to an old AGN that is dead by now.
Yes.
Do you think that with the current data in your survey, you can put some constraints on long time duty cycle for AGN using this technique? Because presumably you have them expanding in size and in spectral index evolves as well.
Yeah, that's one of the motivations actually. People are looking at that, and so they're trying to count essentially how many dead AGN are there out there. And it's still a bit of a puzzle because we don't see so. We see some of them. I mean, I showed you some examples in clusters, for example. There are also some other examples. But if you take the models as they are now and you compute how many you would roughly expect with our current best knowledge, I think you expect to find roughly 10 times more. That's what I heard from these people. So, and they're still missing. So people are now looking at what is essentially missing in the models. There seems to be some ingredient in the models missing, maybe that these things essentially expand more quickly and then they fade also more quickly. So they steepen more quickly than naively if they're confined, for example. So this is people are looking at that, and there's still tension here with serious tension with models here because they should pop up all over the thing if you believe it. AGN.
But you think you can come up with an answer, right?
People think that answer is in the models, and it's not observation. Because before that, people say, "Yeah, you just have to do better work and go to low frequencies, and then you all see them popping up." But we see them popping up, but not in the numbers you expect. I think that's.
I just want to follow up on that. In this Venn diagram you showed of AGN identification, there none of the techniques actually are that consistent. What's the reason for that, and is it understood? And is there which one's the most robust for determining AGN presence?
You mean what to classify a thing as an AGN?
Well, yeah, you showed this one where you had optical, you had radio, you had X-ray.
Yeah,
they didn't agree at all, really. Or the disagreement was larger than the agreement.
I don't think there was really a disagreement. It's just that.
Well, they don't show up in each of them.
Yeah. It's not only. It's also. So this is just in our. I think it was this diagram, right? Yeah. So this is just in our survey area which we observe with LOFAR. So, for example, imagine if only half of the field has infrared coverage. Things do not show up.
So some of it's just because you don't have the coverage.
Yeah, some of things that is coverage. Some of things is because for certain galaxies there's deeper observations, better spectroscopy, so it shows up in the spectroscopic optical sample. So that's just really roughly to get an idea, like in the current survey, like what kind of multi-wavelength matches can you make? And it's not. Yeah, there's also of course problem with identification as well. That also filters in this, but it's yeah, it's a more complicated picture. So it's not, yeah, I wouldn't directly draw a science conclusion from this about our identification. I think the main thing I noted was that the X-ray circle was so small because maybe in the end it's logical, but I didn't expect. I thought that thing would be bigger, but sadly it was not. Yeah, I thought there would be more X-ray AGN known, but apparently it's not the case.
Yes,
I have a question about the first part. When you showed the polarization measurements of the shock relics, the ones where the orientation of the field is more or less perpendicular to the shock surface, did you imply that that is the orientation of the field where the electrons are accelerated as well? Because the general radius of a 10 to the 4 Lorentz factor electron in a micro Gauss field is about 10 orders of magnitude smaller than the size of the relic. So the orientation of the field we see with the polarization is, I doubt, is connected with the orientation of the field where the electrons are accelerating.
Well, it's kind of the larger scale field where these things live in. I'm not sure.
Yeah, but the general radius of the electrons, or gamma factor of 10 GeV, is much, much smaller. It's 10 orders of magnitude.
Oh, yeah, that's on a very small. Yeah, that is on a much smaller scale.
So they don't see really that field, that orientation of the field. They see a field which is amplified on much smaller scales.
Yes, but there still seems to be a kind of uniform thing present, because what we observe, I mean, the coherent emission from like millions of electrons is coherent in that they are polarized. So there seems to be, in that sense, in general, a trend present that there is a field along this way. Yeah.
How do you explain that the field is micro-Gauss, so it's very much amplified from the upstream field?
Now, the application factor from the upstream is a couple. We don't know, but the amplification is only a few, so it's not a lot of. It's a very low Mach number shock, so there's not a lot of amplification or compression.
But the field upstream is of the order of micro-Gauss as well. Upstream.
We don't know, but we think. Yeah. We don't know. We have no measurements, but yeah, we think.
Right.
Yeah. What energy cosmic rays are you seeing?
So the energy of the cosmic rays we see in the radio bands. Those are GeV energies. GeV, yeah.
Is this this playing a role in the general cosmic, producing the origin of the cosmic radiation?
You mean like higher energy cosmic rays?
Yeah, an injection mechanism, is it playing a role there, you think? Or is it,
well, so this is of course GeV, but there are of course also much more energetic particles present in clusters, but so this is essentially set by the magnetic field and the radio emission we observe. So it's kind of, we are sensitive with radio telescopes to GeV particles. That's just how it works out. Cannot do much about that. But it's certainly possible, for example, these are electrons in the radio, but there's also protons, for example, present, and they don't radiate very happily, synchrotron radiation. So so they essentially don't undergo energy losses. So there could be protons probably are protons with much higher energy than is GeV. These are just the electrons we're looking at, but that's why we're forced to look at the electrons. But there are probably very energetic protons present. Once they're accelerated, they just stay there forever. They live for a very long time, and they could be very energetic. So even people speculate that some of the extremely 10 to the 21 EV particles on Earth could come from galaxy clusters. But there are also arguments against that, because actually the galaxy clusters are too distant for that. Because you have the GZA cutoff, for example, which says this is probably not the case. But yeah, very likely they're extremely energetic particles. So this is just a small population of cosmic
probably
rays.
just staying contained in there.
Yeah. But yeah, a lot of the protons are contained, they stay in the cluster essentially. Okay. And they live forever, but sadly we cannot observe them in the radio band. But there are other ways, for example, with gamma ray emission to look for them. And that's why I said that some other models are excluded. People have not seen them yet. They should be there, but at least at current sensitivity levels we have not found them. It would be great if we can detect them, because then suddenly we can study these protons, which carry the bulk of the energy. The electrons are wimpy in that sense.
Right, thanks.
To a novice, it seems as though a lot of what you're learning and going to the lower frequencies is tied to morphology. And I'm wondering whether you consider there to be any sort of confusion problem along the line of sight. In other words, is there any way of knowing that these structures are contiguous versus a superposition along the line of sight?
I think you raise a very good point, and colleagues at conferences, people start complaining about it. You go to low frequencies, everything becomes like a mess and it's complicated, and there are all different populations, they sit on top of each other. It just makes it very complicated. And I think maybe that is a correct comment in some way, because you're looking longer in time, so it becomes more complicated. You have to worry more about things sitting on top of each other. It becomes murky because you have range of eight. So this is actually one of the challenges, like how out of this messy things we see, essentially, because it looks very messy, can we extract the right, still interesting physical thing? So I think we are trying to find our way, like how to address this thing and how even classifying these things, because in the past people relics, halo, you can classify them easily, but now it becomes like messy, and how to deal with that is, I think, something we have to learn. I don't know really. Yeah, so we're trying to find our way in how to do that and what information can we extract and how detailed can you go. At some point, maybe there's a limit to this, because sometimes you don't have to explain every wisp until, and it becomes like, yeah. But we don't know. It's a good
Last question, Tony.
So if we want nice clusters for cosmology that are not recent mergers and that don't have a mess going on and that are kind of serialized, do you think it would really help for them not to be detectable at these megahertz frequencies? Is that sufficient?
The problem is also when you go always deeper, you think you have something nice, then it becomes complicated. Sometimes just you should not always get distracted by the small details. You should kind of read the general textbook. If you can explain that, and then maybe you have explained the physics, and you can. Then it's just a collection of weird animals and things living in the zoo, and then maybe you have But I think it's still worth to really look for a few cases where we can really. There's kind of a nice. We're just lucky in that cluster where we have a fortunate case where something moves at the right moment through something at the right time, where we can then hope to understand the physics, and then we will have a lot of messy cases. So we just have to. Where we can maybe do some statistics. But one of our goals a bit lower, we hope to find some really, by looking at 1,000 clusters, to find some really clear cases where we can maybe work out what was going on there. And for the others, we have to rely to statistics essentially. So there's a bit of a game you can play here. But I showed some examples which I showed. Those were kind of like these single. I mean, there are many clusters in the sky. So I showed a few clusters, like the textbook case. That is an example of like a textbook, roughly binary merger event, where you see this nice symmetric arc, and that's why we learned that this thing really seems to be an outward shock. So we're looking for those kind of cases to pick them out. Yeah.
Let's thank our speaker again.